Good morning, good afternoon. So this is the FRQ number 2. So this is for the AP Physics Mechanics that we are going to be discussing. So let's do not waste the much time and let's come to the screen. So please, yes. So the second question is that we have it, the FRQ, the second FRQ. So in the scenario, the system is composed of the two springs, A and the B, and the block of the mass and the rest on the horizontal surface and the frictionless. So we had a friction between the block and the surface is negligible. So we do not have to be take care of that one. In the spring A, the spring constant is K, and the spring B had the spring constant is 2K. So this had the spring constant is K, this had the 2K. Is relaxed length. Relaxed length means natural length or equilibrium position on that. There is a no compression or there is a no any kind of the potential energy stored in the spring right now. So then we have the next case that they in the figure number 2. So the block is moved to the x is equal to x1 as you can see. So they moved to the right side and held at a rest. So this is the rest position right now. So as you can see, so as you compress this one, this spring get compressed. So some energy gets stored into the spring. That energy we call it a spring potential energy into the system. So I'm going to call it the potential energy of the B, and this is the potential energy of the A. First thing is because this gets compressed by the x1, so this spring is B is compressed. And simultaneously, at the same time, this spring is stretched, or it will also store the some kind of the potential energy inside that. And due to the x1 compression that we have it. So, what is the potential energy? Spring potential energy is the formula for that one is spring potential energy is half kx square. And K is the spring constant. X is you have to keep that in the mind. That is only the stretched length or the compressed length. That is the extension in the spring is how much the extension happen in the spring it is. So you can easily drive that one by the way. Spring potential energy. By the way, in the formula booklet, it is already given over there. So, but if you want to drive it, you can drive it easily. So this is the work done is equal to the force whatever the force into as it is changing position is changing as the force is changing because this is spring force. And if you know the formula for the spring force, that is the kx. I'm ignoring the negative sign for a moment. So this is a dx, and if you integrate that one you will get the kx squared by 2. So this is the uh, work done on the spring when you stretch distance by the x distance of that is half k x squared. That is the spring potential energy stored into the spring is one spring is compressed, so it will store some kind of energy, and the other one is compressed, so it will also store some of the energy. So the point here is first thing is it is x squared. So the displacement, it is negative or the positive, it doesn't matter. So because in the question, what they're asking is to draw the diagram. So the bar, shade the bar to represent the energy of the system for the blocks. So this is the potential energy stored into the spring mass system. So and the second one, the B one, and the K is the kinetic energy of the block that we had to be make the bar for those one. So for that, let's calculate that one first. So what is the potential energy that is in the A? So the potential energy that is in the A, it will be that is half A x. X is the extension, remember it. So it is in this one is x1 square. And similarly, we have the B. So in the B, we have the F. Spring constant is double. This is x1 square. So it come out to be the double the value of the previous one. So whatever that the bar that you're going to make it for the A we have to be make for the term. And now because it is in the, as per the question, it is held at the rest at this position. So there is no kinetic energy over there. So kinetic energy will be zero. So let's make the bar graph. So I have made this stick here, the double of that one, the whatever the potential energy in the A, the potential energy in the B is the double of that. There is no kinetic energy stored into that. So the kinetic energy is zero. So that's why I haven't made any kind of the height over there. So let's move to the B part of the question is, so the block is released from the rest, x is equal to x1, and the begin to oscillate and drive the expression for the v and the block as the block passes through the x is equal to half of the x1. So it is released from the x is equal to x1. At x is equal to half of the x1, you had to be express the velocity. Basically, you have to find out the velocity. As you release it out, it will gain some kind of the velocity as it is going to be approaches to the left side of that x1. Okay. Let's try to understand with the help of the some kind of the animation. So we have the spring mass system. We have the at the x1 position, and it had the spring constant is the 2k. This had the k. So as I release it out, you can see that one, it is going to be gain some kind of the kinetic energy as it is going to be go further. So at this position, as you can see, the stick bar have to be double of that one. The potential energy that is stored into the spring B is the double than the A. So because the spring constant is the 2k. So as you release it out, you can see it is going to be gain some kind of the kinetic energy. So we had to we figure out how much the kinetic energy. So we can apply the total energy conservation. The concept here is, so the concept is, let's write the total energy at the x1 will be. So the E total that I'm going to write it at the x1 position. So that is the potential energy in the A plus potential energy in the B and the kinetic energy. So the potential energy in the A half k x1 square and potential energy in the B that is half. So k value is 2k x1 square and kinetic energy is 0. So if I add both of them, it come out to V2 to get cancel out. So this is 3 by 2 k x1 square. This is the E total at the x1 will be total. When it is going to be come to the this one x1 distance it traveled from here, it will convert to the some kind of the kinetic energy. So the x is equal to half of the x1. We had to find out the total energy because total energy of the system that is not going to be changed. So let me call it x2 position. So total energy E total at the x2 will be potential energy in the A plus potential energy in the B plus potential energy, kinetic energy in the system that we have it. So let's calculate again. So A. So the A have the only the from here, from the equilibrium position, we are going to be measure that one for both of them. So this distance is half of x1. So I'm going to take the half of that. K x1 square plus similarly we have to be right for 2k x1 half of that. Remember it, we always we measure the x distance from the equilibrium position that we have it, how much it is. So the kinetic energy is half mv1 square. So let's calculate this one. This is come out to be 2 to again get cancel out. So this is come out to be 3 by 8 k x1 square plus kinetic energy. So total energy of the system always going to be remain the same. So let's equate the total energy. So total energy at the x1, total energy at this point. So let's equate conservation of the energy. So 9 by 4 k x1 square, and you can divide with the m. This expression with the m, that is v square. And then the v value is going to become out to be, we have to just calculate the speed. So we can ignore the negative sign by doing the square root. We're just taking the positive sign. So that is 3 by 2 in outside of the square root. I take it out, and let's put this one is inside the square root only, and the x1 square also. So this is the ultimately that the speed come out to be at this point is. So in the scenario number one, the block one oscillate with the time period t. So they are talking about only the block in the scenario number one. Okay, the position x of the block in the scenario as the function of the time, they have already drawn it. Okay, so x1 position, so it is being released. So as you can see that when the x position becomes 0 at the t by 4 of the time period. Now it is going to be at the half, it is going to be reached to the x1 position, and then it is at the 3t by 4, it is going to be again reached to the equilibrium position, and at the t time period, the complete time period again at the x1 position. So if I try to demonstrate that one, so this one, so it is going to be reach. So how the system is going to be work, if I to quickly show to you. So as it is, you release it out from here, and at this position, it is the t by 4, and then at the half of the t, and then 3t by 4, and this is the complete t. So the it is going from this x1 coming back to the x1, that is the one time period. Time period is the time taken to complete one oscillation, that is we have the time. So in the scenario 2, the block and the spring system is placed on a new surface. There is a friction between the block and the new surface. Just please note down that one. So there is a friction between the block and that one. And the block is again moved to the same position x1 and released out from the rest. And the block completed the multiple oscillations with the same period as the scenario as one before coming to the rest. So it is coming to the rest. They are already mentioned that. So you have to be keep on decreasing the speed of that. Sketch the graph of the kinetic energy as the block as the function of the time. So the thing is, so you again, this is the, there is a friction force. Right now in this system, I haven't shown any kind of the friction force, it is oscillate. But if there is a friction force, could you feel that the oscillation will be decreased smoothly? This is so it is going to be oscillation, or the period or the amplitude of the oscillation, that is going to be decreased as the time will passes. So this is some kind of the damping oscillation, we call it. So as it will come here, so it is going to be decrease the attenuation. But as you are starting from this position, what there is a some potential energy only in the system that is stored, spring potential energy. So as you release it out, could you feel that? So as initially when you're starting, because as you can see the graph is okay. So I really try to draw the animations. So as you can see this one, so as I'm going to play, so as the how the energies are converting. So at this point you have the, so let me adjust manually. So this at this point we had only the spring potential energy in the system. So as you come to this point, at this point when the at the equilibrium position basically. So none of the spring is stressed. So there is no potential energy in any one of them. So it is only the kinetic energy, the percentage of all the percentage of energy is the kinetic energy. So if I click it over there in the slow motion, so as you can see, it had the how the energies are converting, and we had to be make the graph according to that only. So as you can, this had kinetic energy at this point, all of them. Now the kinetic energy become 0 at this point. So this is the half of the time period. This is the half of the time period. As it is going to become back, as it's going to be come back, and this is 3/4 of the time period. This is the complete time period, one time period. So in that time, if you experience that the kinetic energy is 2 time becoming peak at the t/4, it becomes 0 at the t half, 3t/4, it becomes this one maximum again, and then it becomes 0. So in the one time period, the kinetic energy is becoming 2 peaks, and kinetic energy is always positive. It always shows the peak up only. So let me show you the diagram also. So if I can show you here, so how the things are going to work. If there is no friction force, I haven't enabled that one. So as I release it out from here, so as you can see, it is going peak. So look at that, how the at the t/4. This is at the t/4. So this is the t/4. So the peak value is there. At the half of that, it is going to be reached to this point. So kinetic energy becomes 0. And then at the 3t/4 and the complete time period t. So the oscillations, as you can see. So let's come to our question is, so I had to be pointed out. Let me fastly draw the lines. Or this is t/4, this one. So at the t/4, it's the maximum becomes 0. Actually, this is how it is going to be look like. So at the t/4, so the kinetic energy is maximum. As we discussed this one at the t/2, so it will reach to that point and it will become 0. So you can see some kind of the attenuation. So the time period is the same only. So time period is not going to be changed as they mentioned that one. So it will look like this. Now it will, where the kinetic energy went in the, because there is a friction for the heat energy lost to the surrounding is D. In the scenario number 3, the block is placed with a new block of the larger mass. The coefficient of the kinetic friction between the new block and the surface, this one. So as you place it over there, larger mass, you place it the new block of the larger mass, replace with the larger mass. The coefficient of the kinetic friction between the new block and the surface is the same as the coefficient of the friction between the original block and the surface of the scenario number 2. Okay, that we have made the graph for that one. The new block is moved to the position of the x is equal to x1 and the release from the rest. The kinetic energy of the new block is plotted as the function of the time. Describe how one feature of the graph at the k as the function of the time, the scenario, you could be differ from the graph as drawn it and briefly justify. Okay. So basically, they mean to say that as you place the more heavier mass, what will be the impact on the curve that we have drawn it here? So the time period. So if we look at the time period formula, time period is actually 2 pi square root of the k by m by k. So time period is directly proportional to the square root of the mass. If the mass get increased, so the time period also have to be increased that one. So this is the point that you have to keep in the mind. And even the friction force is going to be increased as the normal force is going to be increased. So the on the mg. So that also that you can note it down. So the more energy get lost in the form of the friction force. So it will be so the peak will drop off more fastly. So this will be the more fastly, but the time period will actually increase. Is that depend upon the mass? So it will look like this, something like this. This is the curve. It will be more sharp drop, and the attenuation more faster, but the time period have to be increased, something like this. So this is the impact on that one, so that you can see. Thank you. So we are going to be make the series of the lectures on the FRQs again. Please subscribe to the channel, and it's free for you. It's very valuable for us. so that we can motivate us and the YouTube become more happy by looking at our content is. We are still improving, so I will appreciate that you give the any kind of the comment or the feedback to how we can improve the things are. Thank you.